All right, welcome to part 2, second period. All right, we're talking about this 1998 problem. So when 2 grams of a sample of pure phenol, 64.98 kilojoules of heat is released when it's burned. So how do I get the molar enthalpy? Zoe said right before the break that that's the amount of heat per mole. This is the amount of heat per how much? 2 grams. So we just need to say then the delta H of the reaction. What do we think? What do we think? What am I going to put?
Product minus reactant.
No, we don't do products minus reactants on this one. Okay? I mean, well, I guess technically we could, but we don't really. To get the molar heat of formation reaction, we don't have to do that. We just simply say, and by the way, we can't do that because we don't have this value right here. Okay, we would have to have this in order to be able to do products minus reactants. So, somebody other than Emmy tell me. Emmy and Reagan have answered everything today. Somebody tell me, what do I do?
Thermochemistry convert moles.
Okay, so I'm going to go, what do I put up, what over what, Nathan?
You put the kilojoules released over 2 grams.
Okay, since it's released, okay, technically it's negative 64.98 kilojoules over 2 grams of C6H5OH. And then how do I go to moles?
And you multiply by 94.12 grams.
Which is what?
That's
The molar mass, right? So we go from grams. Now you could very easily just convert 2 grams to moles separately and then divide it in. Okay? So, but we're just going to go times, what did you say was 94 point?
12.
That's grams over 1 mole. So grams are going to cancel. So this turns out to equal then, how much, Nathan?
Negative
3057.96. Now we have 4 divided by 3. Oh, it's 4 divided by 4 times 4. So how many sig figs should I have? 4, so what should this be? 3,058 kilojoules per mole. Okay? So that's a stoichiometry type problem. You're given an amount, you're given a heat released, here's your conversion factor. Now we have kilojoules per mole. That's again, it's a conversion factor between kilojoules and moles. Now, B, calculate the standard heat of formation of phenol. Now I need to find this value. But now I know delta H, right? Follow me, Ava. So, my negative 3,058 kilojoules, okay, per mole is equal to, what equation do I use? Products minus reactants. This is when you use Big Mama. Okay, so we're going to say 6 moles times CO2, negative 395.5 kilojoules per mole, and I'm going to run out of room, plus 3 times 3 moles times water. And notice that you got to use, they only give you liquid, negative 285.85. Okay, so that is the heat of formation of products minus the heat of formation of reactants. Okay, so it's going to be X plus 0. Okay, and just be technical, 7 moles times 0. Now you would never have to write that, but I'm just kind of making a point. So really, You're just gonna multiply this times that, subtract it out over here. So what do we get? Actually, you're gonna end up, this is gonna be a negative number, so you're gonna end up adding it over here. But what do we get? What they say online, the answer was.
Negative 161.
Negative 161 kilojoules per mole. And the moles are gonna come from this right there. This all turns out to be kilojoules. You have 1 mole here. So the unit's always on delta H or kilojoules per mole. So when we need to find, so this is just one of the variants, the different ways in which you can use the Big Mama equation and just calculating the delta H right here, where you know delta H of the reaction and you have to find the individual heat of formation. Oftentimes this value is given in the wording up here. Very, very good problem right here. This one is one, again, you make sure you know how to do. You have to be able to know how to do this conversion right here. That's asked all the time, even in our calorimeter problems. When you find how much heat is released into the calorimeter for however many grams that you put into there, you have to change that kilojoules per mole. That's this conversion right here. Guarantee that will be asked. On my test, on the AP test. Okay? And then using Big Mama, either products minus reactants to find delta H, or given delta H, find the individual heat of formation of one of the substances in the equation. All right. So then calculate, now that we have, this is the delta H of formation of phenol, C6H5OH. Now it says calculate delta G. What equation do I use for that one? How do I calculate delta G? I don't have any values for delta G. What do I have? You got to find delta S and then use delta G equals delta H minus T delta S. So this is a 2-part, fairly long problem. So we go delta S, and how do I find delta S? Products minus reactants. Okay, so we're going to go 6 times, I'm not going to use units on this one, 6 times CO2, 213.6, plus 3 times H2O, 69.91, minus 1 times C6H5OH, 144, plus, notice again on this one, the oxygen has an entropy. They don't have a delta H, but they do have an entropy. Therefore, it's 205, and then it's 7 times 205. So what does all of that equal? Somebody?
Negative 87.67.
And that's joules per K. Joules per K. Because it's joules per mole K, but we're multiplying by the number of moles, the coefficient. So moles cancels out, so we're left with joules per K. Are you following me every time? Okay? You got one job. Okay? So, what do I do with this number then?
You put it in
Delta G then is equal to delta H, which we said was negative 3,058 kilojoules, okay? Minus the temperature, are we at 298? Yes, we are. times my delta S. Now, can I just put in 87.67?
No,
Why not?
it's in joules.
That's joules. This is kilojoules, so we have to change this to kilojoules. That's a common mistake students forget to do. So it's got to be negative 0.08767 kilojoules per K. So when we calculate all that out, what do we get?
Negative
3,032? And that's good enough. What's point what? No, if that's just what you got there, don't do the point. I didn't know if you just rounded up or not.
Yeah, I just rounded up.
Okay, so that's perfect. Okay? And that's kilojoules per mole. Would this reaction be spontaneous or non-spontaneous? Spontaneous. But yet when phenol is a liquid and I just pour it in a beaker, it doesn't burst into flames. Because high activation energy. But if we light a match, it's gonna blow. Okay? It's gonna go. Well, it's just like burning gasoline. I mean, it's just gonna be a hydrocarbon that's flammable. Okay. Is this the last one? 2003?
Yeah, you just did C and D.
Oh yeah, we gotta go up here. Yeah, this part up here, now we should be able to do this part. 6 grams of carbon and 1.344 grams of hydrogen. We want to get the empirical formula. What do we have to do to get the empirical formula?
It was just C and D for that one.
I know, but I'm just saying, we should know how to do this one. Okay? We should know how to do this. If I have 6 grams of carbon and this many grams of hydrogen, how do I find the empirical formula?
Find how many moles.
Convert it to moles, and then divide by the smallest. Right? So there's 3 steps to finding the empirical formula. Change percent to grams. Well, they already gave you grams. Okay? Change grams to moles, and then divide by the smallest to get the small whole number ratio. Okay? Then once we know the empirical formula, we could, use the information given to use the density, because I would know that it's 7.344 grams total. Use this to get how many liters, let me see, the density of the hydrocarbon is this, it says. What would we do on that? But where is liters anywhere? I would just, once I have my empirical formula, I think that that's all just information that you don't need. The molar mass is just going to be, once you have the empirical formula, okay, you can get the empirical formula mass, okay, and then you have to determine the molecular formula from that. That might be, it's probably a gas. This is pure gaseous. There it is. You got to use gas laws. You have your moles. Okay, you know how much gets made, so you got to use the molar. You got to use your gas law. Molar mass is GERD over PIV on that one. Anyway, coming down here to this. So you just kind of have to work through it. I don't know if you just saw what I just did in my brain, okay? I'm saying, oh, hey, where's liters? We got to get liters in there somehow. They're giving me the density. I need the molar mass of the molecule. So I just had to work backwards and say, okay, what do I need to know? And then I see, oh, it's a gaseous hydrocarbon. I'm going to have to use gas laws to get to liters. And then I can use that to get to my molar mass, because molar mass is GERD over PIV. So you just got to work your way backwards based upon what's given. All right, C and D. Using the information table below. So I have my heats of formation. A 0.010 mole sample is combusted in a bomb calorimeter. Okay? Bomb calorimeter. What goes off in your head?
A bomb.
Hopefully not, hopefully not. What equation?
Negative Q loss, or Q loss equals negative Q gain.
Q loss equals negative Q gain. Now, calculate the amount of heat released to the calorimeter, okay? How do I do that? There's not a whole lot of information given on this one. So I know that much many moles is combusted. How much heat is released to the calorimeter? So I need to do is C, I need to calculate the value of the heat of formation, okay? How do I do that?
I think you're too far down, there's like, there might be.
Is there something else above it?
I think so.
Oh, yeah. So they give me the heat of combustion right there, right? So what equation do I use to find the heat of formation of that one? Part C. Using this data and this information, I need to calculate the heat of formation of this. Big Mama. Delta H of the reaction is negative 4.85 times 10 to the third kilojoules is equal to products minus reactants. 7 times CO2, 7 times negative 393.5 plus 8 times negative 285.8 minus X plus 0. X equals my delta H of formation of the C7H16. It's equal to how much?
Negative 191 kilojoules.
Negative 191?
Yes.
Okay? So that's my heat of formation. That's going to be kilojoules per mole. And there's a 1 mole right there. So when you divide this kilojoules, there's a 1 mole that comes over here that you divide by. That's where your kilojoules per mole comes from. Okay? So there's your answer to C. Now D. If a 0.0108 mole sample is combusted, how much heat's released? So how do I do that? If this is kilojoules per mole, it's super easy. If this is kilojoules per mole, and they tell me how many moles are burning,
Just multiply by the mole.
I just gotta multiply by this. Okay? This is kilojoules per mole. To get to kilojoules, I multiply by moles. Negative 191 kilojoules per mole times 0.0108 moles equals
Negative 2.06.
negative, say that again,
2.06.
kilojoules. Okay? So negative, that's how much is released. Okay, now, because it says released, you don't necessarily have to have the negative sign, because the release tells us the negative sign, but I would just go ahead and just always do it that way. Now, here's a really good question. What does total heat capacity mean? Total heat capacity of the calorimeter. What are the units on it?
Kilojoules per Kelvin, or per.
Per degree Celsius, or it could be Kelvin, either one. Okay? Now, What's not in there? What's in specific heat? What other units in there? That's molar heat capacity, would be moles. Grams is specific heat capacity. Specific heat is the amount of energy it takes to raise 1 gram of the substance, 1 degree. The molar heat capacity is the amount of energy it takes to raise a mole of the substance, 1 degree. The heat capacity, the total heat capacity, is how much energy it takes to raise the whole thing, 1 degree. It just takes mass out of, takes amount out of the system, because calorimeters are almost, they're gonna be the same mass every time. You're gonna put the same amount of water in it every time. So you just calculate the total amount of energy that it's gonna take to raise the whole thing 1 degree. And that's what this value is. Okay? So calculate the temperature. So I need degrees Celsius. So what unit do I need to get rid of? Kilojoules, right? So I'm going to use Q lost equals negative Q gain. Okay? I know now that this is my lost, negative 2.06 kilojoules, is equal to, remember when you have a heat capacity, it's going to be a capital C times T, which is going to equal 9.7273 kilojoules per degree Celsius times the temperature, which is what we're looking for. What is the change in temperature, right? MCAT, C delta T. Okay, so when you have the heat capacity, normally if with specific heat, we say MC delta T, little c. We multiply the mass times the specific heat, and that gets rid of grams. But when you have the heat capacity, you don't have an amount, so you just go heat capacity times the temperature. You just get rid of the mass part. So we just need to divide the kilojoules, this kilojoules by this kilojoules, and we're going to get degrees Celsius. So the change in temperature is equal to negative 2.06 divided by 9.273, and this is negative again, so we're going to make a negative of this. So it's going to come out to be a positive temperature change, which we know if it's burning, temperature is going to go up. So you know you got to have a positive increase in temperature. What does that come out to? And I saw you put in your calculator, didn't I? No? Anyone? No one? 0.222 degrees Celsius. So not very much, because we only had a very small sample. Somebody agree with that number? It's just 2.06 divided by 9.2. It makes it obvious that it's going to be less than 1. Okay? All right. What I would take away from this, I would on your sheet, I would circle or highlight, underline in your notes. If you didn't print the sheets out, I would make a note. Total heat capacity is just capital C times delta T. Okay? Total heat capacity. If it's specific heat, it's MCAT. If it's molar heat capacity, then you just multiply by moles. You change grams to moles. Instead of MC delta T, it's moles C delta T. Use the units to direct you as far as what you need to do. Yeah.
For part 1 of D, I used the wrong values. Like, why did you use the heat of formation instead of the heat of combustion?
Well, I may have used the wrong one because I do that all the time. To calculate the amount of heat released, we should have used this one. Oh, crap. Now you just tell me.
I didn't know if I was wrong.
I know, but that's a great question to ask, okay? Because This right here is the delta H of reaction. It's supposed to be the delta H of the reaction. But what did I put in there? The delta H of formation. I need to be using that number in here. 4.85 times 10 to the third, which then changes this number, Emmy, to what?
I have -87.3.
Okay? So then that number comes down here to -87.3, which changes this number to equal really important. This is delta H. Know what your values are, and obviously it's very confusing. I mean, I just made the classic mistake, used the wrong value. Because it's the one we just calculated, I assume you use it on the next one. I just didn't think. Okay? I just blindly went to the next step. That's when you get in trouble. Think about what you found. Think about what the equation asks for. Delta H of the reaction. Well, this is heat of formation. This is delta H of the reaction. How many did you get a new answer?
Check it
9.4144.
Okay, so 9.41. Okay? So, I highlighted a very common potential mistake. I would love to say I did it on purpose.
We're just gonna act like you did.
Yeah, I should act like, oh, that's right, that's a classic mistake. We gotta make sure we don't do that. That's why, I'm trying to, no, but I just made the classic mistake, okay? I'm not gonna try to sugarcoat that one. All right. Break.
There's just so much work.
It's
Oh,
so cool pouring it apart.
You like the sound? Yeah.
Sounds good.
It gets a little obnoxious for the rest of the stuff. Okay, so here's an old stoichiometry problem. So since we have a few minutes left here, let's just flash back to, I know, we're done. This is just now, just something I want you to do in your notes, just right now. This is 2004. So if I'm given 11.5 liters and it says calculate the number of moles, what equation am I gonna have to use if I'm given a gas, 11.5 liters, 2.66 atmospheres, 298 K? How do I find moles?
Ideal gas law.
PV equals nRT, N equals PV over RT.
Yeah.
And then identify the limiting reactant. part C says calculate the number of moles of Fe2O3 produced. Straight up stoichiometry. Once you have the limiting reactant, figure out how many moles of Fe2O3 you produced. Fe2O3, by the way, is the red powder that we use to make the thermite. Which I used it all up on y'all, and so Monday, Thursday, people, I gotta order some more before I can do it for them live.
So they get to do it on your break.
That's right, Ed.
Is part C in grams or in miles?
Moles.
Okay.
Calculate the number of moles produced. What do these come out to? Let me see. 1.34, I should do that in my head, divided by 2. 0.67. Is that what you guys got? Yeah? Okay, divide by the coefficients from the equation. The equation's given, I'm gonna mess it up, but there's the equation. Okay? It's 2 and then 3/2, so which one's my limiting reactant? This is my limiting reactant. Okay? So this is the answer to A. This is the answer to B. Okay, support your answer with calculation. Dividing by the coefficient, smallest number, that's sufficient calculation. Okay, now C says how many moles of Fe will be produced. Well, we have 1.34 moles of Fe times, when we look at the equation, okay, the equation says that for every 2 moles of Fe, I'm going to make 1 mole Fe2O3 for every 2 moles of Fe. So really, I already know that number. It's going to be 0.67 moles of Fe2O3. Okay? So that's part C. That's all stoichiometry. That's getting us to where we have the values that we need to do the rest of it. Okay, so you have all those numbers written down. So then it says D. .67 moles. Calculate the standard entropy of formation. Well, I know that delta G is this, right? They want delta S. They don't give me any of the entropies, so what equation do I have to use?
Well, you gotta find delta H.
Say that again?
You gotta find delta H.
Well, no, we don't really have to find delta H, because if you go back and look, delta H is given. This heat of formation is the same as the delta H of the reaction, because it's a formation reaction. So I know that delta H of my reaction is equal to negative 824 kilojoules per mole. I know delta G now is given as keep going. Delta G is equal to, I just saw it, negative 740. So how do I find delta S? What? What formula?
Delta G equals.
So negative 740 is going to equal negative 824 delta H minus temperature. We're at 298 because it's here standard, times delta S. And again, it's a formation reaction, so delta S of the reaction. So delta S is going to equal
Negative 282 joules.
okay? So it comes out to 0.282 when you just do this, right? And that's kilojoules per K, which is going to equal 282 joules per K.
It's
Negative. Okay? Now, so part 2, which is more responsible for the spontaneity of the formation? Look at here, we got negative and negative again. Which one's driving the reaction?
Delta H.
Delta H, enthalpy. Okay? All right, I'm hoping I can get this next one. Okay, so we're given here, we're given 2 reactions, X and Y. Now I don't care about any of the parts except the very last one, but I'm gonna go reaction X is equal to 1/2 I2 solid plus Cl2 gas, 1/2 Cl2 gas makes ICl gas. And delta H is equal to 18 kilojoules per mole. Okay? Now, I had to write that down because I'm gonna move this up, so we had to make sure we remember that. So now it says, F. For the vaporization of iodine, solid iodine to I2, actually, this is supposed to be gas right here. It's a typo. The value of delta H is 62 kilojoules per mole. Using this information, calculate the value for this equation. Any suggestions? Okay, except this is a gas and this is a solid.
A negative. It will be negative 62 kilojoules, I guess.
That's just the iodine to the gas part. They want the overall heat of this reaction.
Well, I guess for.
This is supposed to be an equals, or goes to, it's supposed to be an arrow. You got two equations. What do we do with two equations? Hess's law. Okay? We got to use this equation right here to get rid of change the solid to a gas. Okay? So since I have solid on this side, okay, I need solid on the other side to cancel it. Okay? So I'm going to say I2 gas going to I2 solid. So my delta H of vaporization, it's not vaporization anymore, it's deposition, but it's going to equal what? Negative 62. So now, what else do I have to do to this one? Multiply this one by 2, which means I have to multiply this by 2 to get to 36. Okay? So now, I can say that the I2 solids will cancel, and so you end up having I2 gas plus Cl2 gas goes to 2 ICLs. So what's delta H going to equal?
Negative 26.
Negative 26? Okay, so what's my clue here? What's my indicator? Well, I'm given an equation. I'm given this equation. I'm given multiple equations. So I have this equation here. I'm trying to find a final equation, and I'm given those equations previously. That's going to be a clue. I need to use Hess's law. And you just want to get to where those cancel out, and we add them together. So we looked at really pretty much just about every type. There really, in all of these, there weren't a calorimeter problem. But notice that in the 2018, 16, 15, 14 that we did, almost all of them were calorimeter problems. And so it kind of shifted. So calorimeter problem is probably the most important one to focus on. But on all of these, we've seen how they ask them in a variety of different ways. Okay? Lots of information today, but hopefully it can help clarify how to do some of these problems, some of the things to look for. It's going to be Princeton Review on Monday, test on Tuesday. Okay? Princeton Review on Monday, and you'll scan it. You guys will be at home, you'll scan it. I don't know if I'm going to sign the whole thing or just parts. We're just going to go from there. All right.